knowledge, truth, and lies. So far in this chapter we have explored the ways in which distributed systems are different from programs running on a single computer. There is no shared memory, only message passing via an unreliable network with variable delays, and the systems may suffer from partial failures, unreliable clocks, and processing pauses. The consequences of these issues are profoundly disorienting if you're not used to distributed systems. A node in the network cannot know anything for sure. It can only make guesses based on the messages it receives or doesn't receive via the network. A node can only find out what state another node is in, what data it has stored, whether it is correctly functioning, etc., by exchanging messages with it. If a remote node doesn't respond, there is no way of knowing what state it is in, because problems in the network cannot reliably be distinguished from problems at a node. Discussions of these systems border on the philosophical. What do we know to be true or false in our system? How sure can we be of that knowledge if the mechanisms for perception and measurement are unreliable? Should software systems obey the laws that we expect of the physical world, such as cause and effect? Fortunately, we don't need to go as far as figuring out the meaning of life. In a distributed system, we can state the assumptions we are making about the behavior of the system model and design the actual system in such a way that it meets those assumptions. Algorithms can be proved to function correctly within a certain system model. This means that reliable behavior is achievable, even if the underlying system model provides very few guarantees. However, although it is possible to make software well behaved in an unreliable system model, it is not straightforward to do so. In the rest of this chapter we will further explore the notions of knowledge and truth in distributed systems, which will help us think about the kinds of assumptions we can make and the guarantees we may want to provide. In Chapter 9 we will proceed to look at some examples of distributed systems, algorithms, that provide particular guarantees under particular assumptions. The truth is defined by the majority. Imagine a network with an asymmetric fault. A node is able to receive all messages sent to it, but any outgoing messages from that node are dropped or delayed. Even though that node is working perfectly well and is receiving requests from other nodes, the other nodes cannot hear its responses. After some timeout, the other nodes declare it dead because they haven't heard from the node. The situation unfolds like a nightmare. The semi-disconnected node is dragged to the graveyard, kicking and screaming, "I'm not dead." But since nobody can hear it screaming, the funeral procession continues with stoic determination. In a slightly less nightmarish scenario, the semi-disconnected node may notice that the messages it is sending are not being acknowledged by other nodes, and so realize that there must be a fault in the network. Nevertheless, the node is wrongly declared dead by the other nodes, and the semi-disconnected node cannot do anything about it. As a third scenario, imagine a node that experiences a long stop-the-world garbage collection pause. All of the node's threads are preempted by the GC and paused for 1 minute, and consequently, no requests are processed and no responses are sent. The other nodes wait, retry, grow impatient, and eventually declare the node dead and load it onto the hearse. Finally, the GC finishes and the node's threads continue as if nothing had happened. The other nodes are surprised as the supposedly dead node suddenly raises its head out of the coffin, in full health, and starts cheerfully chatting with bystanders. At first, the GC node doesn't even realize that an entire minute has passed and that it was declared dead from its perspective. Hardly any time has passed since it was last talking to the other nodes. The moral of these stories is that a node cannot necessarily trust its own judgment of a situation. A distributed system cannot exclusively rely on a single node, because a node may fail at any time, potentially leaving the system stuck and unable to recover. Instead, many distributed algorithms rely on a quorum, that is, voting among the nodes. See quorums for reading and writing on page 179. Decisions require some minimum number of votes from several nodes in order to reduce the dependence on any one particular node. That includes decisions about declaring nodes dead. If a quorum of nodes declares another node dead, then it must be considered dead, even if that node still very much feels alive. The individual node must abide by the quorum decision and step down. Most commonly, the quorum is an absolute majority of more than half the nodes, although other kinds of quorums are possible. A majority quorum allows the system to continue working if individual nodes have failed. With 3 nodes, 1 failure can be tolerated. With 5 nodes, 2 failures can be tolerated. However, it is still safe, because there can only be one majority in the system. There cannot be 2 majorities with conflicting decisions at the same time. We will discuss the use of quorums in more detail when we get to consensus algorithms in Chapter 9. Frequently, a system requires there to be only one of something. For example, only one node is allowed to be the leader for a database partition. To avoid split brain, see handling node outages on page 156. Only one transaction or client is allowed to hold the lock for a particular resource or object, to prevent concurrently writing to it and corrupting it. Only one user is allowed to register a particular username, because a username must uniquely identify a user. Implementing this in a distributed system requires care. Even if a node believes that it is the chosen one, the leader of the partition, the holder of the lock, the request handler of the user who successfully grabbed the username, that doesn't necessarily mean a quorum of nodes agrees. A node may have formally been the leader, but if the other nodes declared it dead in the meantime, for example due to a network interruption or GC pause, it may have been demoted and another leader may have already been elected. If a node continues acting as the chosen one, even though the majority of nodes have declared it dead, it could cause problems in a system that is not carefully designed. Such a node could send messages to other nodes in its self-appointed capacity, and if other nodes believe it, the system as a whole may do something incorrect. For example, Figure 8-4 shows a data corruption bug due to an incorrect implementation of locking. The bug is not theoretical. HBase used to have this problem. Say you want to ensure that a file in a storage service can only be accessed by one client at a time, because if multiple clients try to write to it, the file would become corrupted. You try to implement this by requiring a client to obtain a lease from a lock service before accessing the file. Figure 8-4, incorrect implementation of a distributed lock. Client 1 believes that it still has a valid lease, even though it has expired, and thus corrupts a file in storage. Figure 8-5, making access to storage safe by allowing writes only in the order of increasing fencing tokens. The problem is an example of what we discussed in process pauses on page 295. If the client holding the lease is paused for too long, its lease expires. Another client can obtain a lease for the same file and start writing to the file. When the paused client comes back, it believes incorrectly that it still has a valid lease and proceeds to also write to the file. As a result, the client's writes clash and corrupt the file. When using a lock or lease to protect access to some resource, such as the file storage in Figure 8-4, we need to ensure that a node that is under a false belief of being the chosen one cannot disrupt the rest of the system. A fairly simple technique that achieves this goal is called fencing, and is illustrated in Figure 8-5. Let's assume that every time the lock server grants a lock or lease, it also returns a fencing token, which is a number that increases every time a lock is granted, for example incremented by the lock service. We can then require that every time a client sends a write request to the storage service, it must include its current fencing token. In Figure 8-5, Client 1 acquires the lease with a token of 33, but then it goes into a long pause and the lease expires. Client 2 acquires the lease with a token of 34. The number always increases and then sends its write request to the storage service, including the token of 34. Later, Client 1 comes back to life and sends its write to the storage service, including its token value 33. However, the storage server remembers that it has already processed a write with a higher token number 34, and so it rejects the request with token 33. If Zookeeper is used as lock service, the transaction ID ZZ or the node version C version can be used as fencing token. Since they are guaranteed to be monotonically increasing, they have the required properties. Note that this mechanism requires the resource itself to take an active role in checking tokens by rejecting any writes with an older token than one that has already been processed. It is not sufficient to rely on clients checking their lock status themselves. For resources that do not explicitly support fencing tokens, you might still be able to work around the limitation. For example, in the case of a file storage service, you could include the fencing token in the file name. However, some kind of check is necessary to avoid processing requests outside of a lock's protection. Checking a token on the server side may seem like a downside, but it is arguably a good thing. It is unwise for a service to assume that its clients will always be well behaved, because the clients are often run by people whose priorities are very different from the priorities of the people running the service. Thus, it is a good idea for any service to protect itself from accidentally abusive clients. Byzantine Faults. Fencing tokens can detect and block a node that is inadvertently acting in error, for example, because it hasn't yet found out that its lease has expired. However, if the node deliberately wanted to subvert the system's guarantees, it could easily do so by sending messages with a fake fencing token. In this book we assume that nodes are unreliable but honest. They may be slow or never respond due to a fault, and their state may be outdated due to a GC pause or network delays. But we assume that if a node does respond, it is telling the truth. To the best of its knowledge, it is playing by the rules of the protocol. Distributed systems problems become much harder if there's a risk that nodes may send arbitrary faulty or corrupted responses, for example. If a node may claim to have received a particular message when in fact it didn't. Such behavior is known as a Byzantine fault, and the problem of reaching consensus in this untrusting environment is known as the Byzantine general's problem.